This is Module 7, Part 2 or B, Chemistry. So, I'm going to hand you your Module 7 test today, and ordinarily you wouldn't get it till next week, and then you turn it in the following week, but in terms of the number of Thursdays we have in a month, this is the way we got to do it. So this week you'll take home the Module 7 test, but you'll also be finishing your homework if you do it according to the schedule. Some of you are ahead, some of you are behind. But anyway, if you're doing it according to the schedule, you will finish your Module 7 homework, the rest of this week, early next week, and then take the test just prior to coming next week. You got to get all your stuff in next Thursday. I need it all right? And I understand that, that's a struggle for some of you, so speak to me if you've got issues. But it's all due next Thursday, so I can get your folks your grade, your first semester grade. And I will include for you today in the handout an extra credit option. There's 10 points if you do this thing, and it is, in terms of chemistry, there's probably not a lot here for it. It's a reflection of the day job. I've done this as long as I've been teaching, about 10 years now. Extra credit in the fall, extra credit in the spring. It's 10 points, pretty significant as a matter of fact, because I'm just curious about what you think and what you believe. And all it is for me is a sort of a sampling of the Christian faith out there. I presume that most of you here are believers. It's entirely possible that some of you are not. I've taught unbelievers in the past. You can still get the extra credit if you're not a believer. You're just going to answer for what you perceive to be the case for believers. So this is not a discriminatory thing. All it is a survey of what you think. And that's perhaps the most important part of this, is that if you do this thing, if you want the extra credit, it's a half page, handwritten, maybe less, quarter page, half page, typewritten, of what you think and believe, not what you expect, what you might think I would expect or want, or anyone else, just what you think, okay? So I'll send that along in just a minute. I'll pass them all out. We launched into Module 7 last week, and it's a bit of a thick module. So I wanted to get right to it today and sort of back up a little bit in terms of where we were. So if you would, turn to page 207. Let's do it that way. And we'll back it up to there. Actually, let's go to page 205. It's really your notes, but that's kind of where it is in the textbook, and so it'll re-familiarize yourself. Good morning. So, on page 1 of your notes, remember, in terms of atomic number, remember what we introduced with regards to atomic number, and that is, it tells you how many protons you have, and a number of electrons, as a matter of fact, in a particular given element. So, if helium is number 2, the atomic number 2 tells you that you have 2 protons and 2 electrons, and that's generally the case. We're going to discover exceptions, as we always do. In terms of electrons, we're going to see electrons moving around and that sort of thing. But protons stay the same, and so in terms of your definition, the atomic number tells you how many protons it contains, and that is a true statement all of the time. We identified electrons and protons and neutrons as just particles that make up the atom. We also identified isotopes, and I encouraged you to read the section with regards to the enrichment of uranium. We just don't have time to go into it, but it reflects the fact that elements exist naturally with different numbers of neutrons. Ordinarily, at least, and this is actually not a true statement, ordinarily is not necessarily the truth, because again, in certain percentages, all elements have different numbers of neutrons, at least some. make that sum. Elements have different numbers of neutrons. So you can be carbon and have 6 neutrons, or you can be carbon and have 5 neutrons. All right. So that's the reality of an isotope. Atoms with the same number of protons, but differing numbers of neutrons. And those differing numbers of neutrons, remember what we said, for the most part, the isotopes behave identically chemically. The only difference between them is their mass, because neutrons have mass, and so those that have less neutrons will have less mass. Turn over to page 2 of your notes and page 209 of your textbook. So we introduced it last week. We kind of ran through it. I asked you to look it over. Not that it's that important, but the Rutherford or planetary model we're going to introduce. But look at page 209 and look at the plum pudding idea of the atom. That was the thinking for a while until experimentation changed that. Remember in the statement here on page 209, remember, it's impossible to see atoms, thus chemists had to imagine what the atom might look like. That's still the case. We can't see atoms. We see them through an electron scanning microscope. We're not seeing them. We're seeing an image created by a computer based on data fed to that computer. So that's what was thought to be the shape and form of an atom for a while. And the plum pudding model, in other words, you had sort of an electron goo. That was the pudding. And then you had, the positively charged pudding. That was the protons, and then the electron plums kind of floating in that stuff. We'll turn over to page 211, and there we introduced the Rutherford model, and he came up with, and again, in terms of the experimentation, it's interesting. The history's always interesting, but we just don't have time to do it. The Rutherford model, or the planetary model, is the idea that you have a nucleus with protons and neutrons in the middle, sort of like Earth, and then, well, maybe make that the sun. You could use the moon on that, I suppose. But you have the sun in the middle, and then the Earth orbiting in the form of electrons. Okay, so that's the Rutherford model, and again, the nucleus, top of page 2, defined as the center of the atom with the neutrons and the protons. So that's roughly, and on page 212 again continues the discussion of the Rutherford model and how he came up with what he came up with, and it is interesting in terms of the firing of alpha particles, what he believed to be alpha particles or electrons through this thing, and then bouncing off the center in terms of the nucleus, and that's how he figured out that that there's something there in the middle. And so just a fascinating discussion. Then last week before we quit, we introduced the concept of the nature of light. And we talked about the particle wave duality theory. And the reason we talked about that is because no one is absolutely certain of what light is. It behaves in 2 different categories. It behaves as a particle, in other words, like a photon. That is what is the name for light particles. But it also behaves like a wave. So that gives rise to the particle wave duality theory, the theory that light sometimes behaves as a particle and sometimes behaves as a wave. It likes to surprise you. All right, that's all it does. So sometimes it looks like a particle, sometimes it doesn't. And so in terms of that discussion, in terms of the nature of light, we then introduced the whole concepts of waves, and we sort of reminded ourselves, most of you have been to the beach, maybe some of you have been to a lake, and there's been at least some waves there. Hey, Liam and Lily, welcome. So we introduced the concept of waves, and we introduced several terms to describe those waves. The wavelength is the distance between the crests and the troughs. On page 214 is figure 7.7. Sort of a helpful reminder. It's not in your notes. It's something you could easily draw, actually get a point of extra credit that way. But notice what the wavelengths are. Of course, they're at the crest there in this picture, but they're also at the trough at the bottom. Of course, trough is identified as the dip at the bottom. And again, if you've been at the beach, you know the crest is, if you're a surfer or even a body surfer, you want to hit the crest and ride it in. The trough is what's in between. The amplitude is the measure of the height of the crest or the depth of the trough, and that's indicated there also in terms of your figure 7.7. They have a wave that is ending different or beginning different, depending on how you read it, than the other waves, and so the amplitude is the top to the bottom. Ooh, that's a gnarly wave, dude. So that great big wave that you wanted to catch, that has to do with amplitude. Now, relating this, and we're also going to talk about frequency today. In fact, we're going to introduce it fairly quickly. And to your great delight, I know how you look forward to the formulas. Oh, we have another formula today. Or as Mr. Krabs says, formular. So we'll look at that in just a moment. But in terms of relating this stuff to stuff, all right, we introduced, just as before we walked out the door last time, Roy G. Biv. All right, that's your buddy Roy G. Biv. And all Roy G. Biv is an acrostic that reminds you of the nature of light as it relates to its wavelength. So Roy G. Biv is red, orange, yellow, green, blue, indigo, and violet. You see that on the page of 215. And then you also notice in terms of that, this is the discussion that we're going to have in just a second in terms of nanometers, all right? Nano means 10 to the minus 9, all right? And so the wavelength in this instance, and I'm just reading from your textbook, the red light's wavelengths, as you can see, in terms of 700 nanometers, that means it is very, very small, all right? Its wavelength is very small. Of all the colors, though, red has the longest wavelength. Look at that. Violet is 400 nanometers. So even though we're talking about 10 to the minus 8 in terms of a wavelength, and it's only 700 for red, well, violet is even less, okay? So that's the discussion there at the bottom, and what you perhaps would be, what would do well to think about and remember in terms of this stuff. So we're talking about wavelength of the visible spectrum, what you can see with your eyes, and some of you are colorblind, so you can't see that. But in terms of what you can see, that is the visible spectrum. Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. All right, so I think that's where we quit last time. Let me see if there was any questions about that stuff. And if not, we're okay. We got a lot to do yet, and I got stuff to hand out to you and receive your homework. Well, you know, I guess we'll do the best we can on that, but I'd like to give you tests back today. Most of you have done fine, you've done okay or fine. A couple of you have had some struggles with some of the tests, so I want to give them back to you, and if you want to correct them, that's our deal, right? If you're able to correct them and learn the material and get them back to me, I'm glad to update your grade. I'm also glad to discuss the stuff that you didn't understand. The test reflects that. If you missed the questions on the test, you didn't get it, right? So if you're willing and you want my help, all you gotta do is call or email, and I'm glad to work you through that stuff. Tests, you know, they're hoops to jump in terms of grades and future and that sort of thing. But what they should be, both in school and in life, is just a measure of what you need to learn. You know, I didn't get that, so how can I get that the next time? If you want to improve your grade, let me know. So we'll get that stuff back in just a minute. All right, here we go. Physical constant. That's defined on page 216, but I have it for you in your notes. A physical constant is a measurable quantity in nature that does not change, okay? So we will talk about physical constants throughout the rest of the course, and we'll talk about one in just a moment. So frequency, if you would, we're looking at page 217, but turn back to page 214 and look at your handy little drawing there, figure 7.7. So frequency is the number of wave crests or troughs that pass a given point each second. All right? So the frequency of a wave then has to do with well, and so how about a given point is the figure 7.7 tidal. So the number of waves that pass by that tidal in a certain period of time describes its frequency, right? So if you're at the beach and you're trying to catch a wave, well, depending on what kind of body surfer or surfer you are, you might want quite a bit of time in between them waves to get ready. On the other side of the coin, you might be okay, so you're just ready for anything at any time. So the frequency, of course, has to do with the number of waves hitting you as you are preparing to surf in. And so the fewer, the smaller the frequency, the smaller the number of waves coming through, right? So that's all the frequency is. It's the same definition as it is in terms of life, only attributed then to waves. We're going to apply that in just a second and make some statements about frequency, which you will again immediately intuit because it's pretty straightforward. But in terms of hertz, what is a hertz? And the standard frequency in terms of hertz is simply 1 per second. Let me make sure that that's a real nice definition, tight definition for you. We'll go to the back here, and of course it is not there. So if you would, next to the word hertz, Heinrich Hertz is the name of the guy who discovered this, but all I want you to do is put 1 per second. All right, right next to that, because that's what we're going to describe hertz as, 1 per second. All right, 1 per second, 1/s, 1 per second. Now, here's our fabulous formula for today. So frequency, in terms of the number of those waves that's passing a given point at a given time, which is 1 per second. Frequency, it's measured, its unit is 1 per second, is equal to the speed of light, and this is what we're speaking of, again, not waves on the beach, but light, is equal to the speed of light. There's your physical constant today, all right? I mentioned to you we'll use physical constants throughout the rest of the course, but today's selection is the speed of light, and it's 3.0 times 10 to the 8th meters per second, all right? That's the unit for the speed of light, divided by the wavelength, all right? And again, that's either in meters or nanometers, and nanometers is 10 to the -8th. All right, so to determine the frequency of something, all you're going to do is divide the speed of light, which is always 3.0 times 10 to the 8th meters per second, by the wavelength. All right, so it's a very simple formula, a simple division problem, and if they give you the frequency and they want to know the wavelength, well, you just got to move the formula around a little bit. But there's an example on page 7.2. A violet light wave has a wavelength of 405 nanometers. That's good. What's its frequency? It's just as simple as dividing the 3.0 times 10 to the 8th by the 405 nanometers, all right? You might have some challenges with messing around with the units, but we're not going to spend any time on it because it's just a simple division problem. So is there any questions about that fabulous formula there? It's very simple. As a matter of fact, we don't spend a lot of time on it. I'm just going to tell you that straight up. Is there any questions about it? Okie dokie. Let me make these statements. Turn to page 219, but also then look at the bottom of your notes. I have encapsulated statements from page 219 and page 220. And instead of looking actually right now at page 219, turn back. Go back in time to page 214 and look at the figure one more time. All right? So here are the statements. When wavelength is large, so there you see wavelength, frequency is small, right? Does that not make sense? So if there's a long distance between the wavelengths, then you know the frequency is not going to be very frequent, all right? And then the opposite, when wavelength is small, frequency, thanks to my notes, is large. And that makes sense too, right? So if the wavelength is close together on your little picture there, in other words, if you had the ability to move those crests or those troughs together, you would be decreasing the wavelength but increasing the frequency, right? So again, these are intuitive statements, but you also kind of got to file them a little bit. You got to think about it for a second. Next one. A light wave's frequency, as a light wave's frequency increases, its energy increases. All right? So if you don't like to body surf or to surf, and you're just going to go and put yourself in the water there at the beach, all right? And you're just standing there, and in comes a wave, and in comes a wave, and you're just having a great old time. There's another one. Oh, there's another one. But all of a sudden the weather starts to change and those things start to come faster. All right? What happens to you? Well, you're not having as good a time, right? Because who wants to get battered by waves? All right? But what's happened, of course, is the frequency has increased. You're getting hit more often. And what does that mean in terms of your movement? Well, you know what that means. You're moving more. That is a reflection of energy, right? The fact that you're moving more. Think of waves in a storm and a boat, all right? Again, if any of you have ever had that sort of thing, you want to either get your boat out of the water or you want to secure it, because waves can batter something if the frequency is high enough because the energy is high, right? That's the statement. As a light wave's frequency increases, its energy increases, all right? And as its frequency decreases, oh, that's better, then its energy decreases, all right? Last statement, and then I'll see if you got any questions about them. As a light wave's wavelength increases, and all we're doing is relating frequency to wavelength, all right? We started off by relating those two. Now we're relating wavelength to energy. As a wave's wavelength increases, its energy decreases, right? Because again, all we're doing is talking about the number of waves and also the distance between the troughs and the crests. Likewise, as its wavelength decreases, its energy increases. So as the wavelengths get smaller, the frequency gets larger, and the energy increases as well. All right. So what you got there is a lot of sort of they're not contradictory statements, but they're using opposites. And sometimes that's confusing. So is there any questions about that stuff? Anything at all? It's also intuitive. Like I say, you live life, you know these things. If you've ever been to a beach or, that's just the best illustration, I suppose. You understand that stuff. All right, we're still doing okay. Turn over to page 3 then. And we are, let's see, we're to Planck, alrighty, and the page 219 describes wavelength and frequency in terms of the various wavelengths on the electromagnetic spectrum. In other words, the non-visible spectrum of wavelengths, of light wavelengths, and you see that gamma rays there are at 20 hertz. AM radio is at, 10 to the 20th hertz. AM radio is at 10 to the 6th hertz. Gamma rays, obviously the frequency are considerably more, as are X-rays. You can relate to X-rays. You don't want to you don't want to stand in there and get X-rayed on a continuing basis. Why? Because the energy is so high, even though you might not feel it at the time, the energy is so high and then therefore damaging to tissue. Same thing with ultraviolet light. Look at the look at the frequency there in terms of the ultraviolet light, and you know that as well. If you lay out too long at the beach, you have a good dose of the high frequency ultraviolet light, and you know what it does to your skin. Then there's the visible spectrum. Then there is the spectrum that is less infrared, microwave, radar, and again these can be dangerous even though they are lower frequency in terms of our health. So now page 221. So we got Planck and his constant here. So in terms of introducing this, really this is not what I want to spend a lot of time on, so let's just introduce it and we'll be done with it. So the symbol H refers to a physical constant. It's called Planck's constant. Let's just do the notes, and this is what you're responsible for on the test anyway. So whatever I have on the notes, if you're familiar with this, you're going to be fine. So the energy of a light wave, capital E in terms of a formula. H is Planck's constant. There's another constant for you today. We introduced to you the speed of light. Well, we got another one, and that's Planck's constant, 6.63 times 10 to the minus 34 joules per hertz, times the frequency of whatever that light wave might be. That is a formula for energy to determine the amount of energy in a given wave. And there's some examples there on page 222. I might come back to them, but we got to get to this other stuff before we do that. So interesting discussion about rods and cones there. Again, that's something for you to look through. This is not really an anatomy course. So here's the notes that I want you to be familiar with. By adding energy, heating or passing electricity through atoms, light is emitted. All right? So when you add energy to any atom, all right, there is a glow, a color. And next statement in your notes. Each element or atom emits its own unique wavelength of light, and therefore elements can be identified, I'm sorry for the mess up there too, can be identified by measuring the wavelength of the light emitted when heating. From my high school chemistry course, there's two things I learned. And both of them were from lab, and you don't have a chem lab. So one of them had to do with rinsing out bottles. And you know, I've searched this and I still can't find the concept. I don't know if this guy was out there or what, but at some point in time, good morning, he explained that if you want to rinse a bottle out, you know, you got some soap in a bottle and you want to get that soap out of there. Do you fill the bottle all the way up, or you just put a little water in there and do that several times? Do you fill it all the way up a bunch of times, or you just put a little water in? It turns out, and I can't even tell you the reason for the chemistry. I think it has to do with the chemical reactions between the water and whatever you're trying to rinse out. But The bottom line is I learned that you just use a little bit of water and then do that several times, and it's more effective in rinsing a bottle. And the second thing is what we're going to talk about now. They had Bunsen burners. They had gas available at a big chem lab in this high school. And so we would take little pieces of elements and hold them over the fire, and lo and behold, they would emit a color, and we would compare that color to actually there was some sort of a page or something, and we could determine pretty well what those elements were, even with our naked eye, even without the use of a spectrometer, which we're going to introduce in a second. You hold that puppy over the flame, and there it was, a pretty color, and it was unique to each element. So I tried that with my finger, and it didn't work. So, but all right. So each element emits its own individual color. A spectrometer, that's the next statement in your notes, analyzes the light emitted by substances, matching elements to their individual wavelengths. Spectroscopy is a method of analysis, and it's applied to chemicals and stars and a number of other things. So you've heard scientists make statements which maybe you thought were kind of arrogant and cocky. Here we are, however many light years away from this distant star, and they say, oh, well, that's made out of da-da-da-da-da, all right? And you said, how can that possibly even be? Reason why they have a pretty good idea of what was being emitted off of that star is through the use of a high-powered spectrometer and telescope analyzing the colors that are in the process of reflecting the fact that stuff's being burned, all right? So identifying the various elements a good distance away, and of course we can do the same thing in a chemical lab. Is there questions about that? About the idea of an individual color being emitted when you add energy to a given element. Incidentally, there's a reason, and there's an aspect to this which we will discuss in the next module, but right now all I want you to know is that if you heat it up, it's going to show a color. All right, an individual element will show its own unique color. All right, we good? Dookie dokie. Next statement on your notes. Well, actually, turn over to page 226. There, ladies and gentlemen, is the Bohr model. Bohr. That's the Bohr model of the atom. And so what's happening is we're getting a little further down the line from Rutherford. We're getting a little more sophisticated. And there's the Bohr model, which says, look at the nucleus there, which contains protons, that's the red things. The neutrons, that's the blue. And those little balls and little dotty things circling around the thing are electrons and something new, possible orbits for other electrons. As it turns out, there are other orbits. The Bohr model, back to your notes, middle of page 3, when electrons move, Bohr model puts neutrons and protons together in the center of the atom, the nucleus, and suggested that the electrons can jump into and out of orbits by absorbing energy, but now this is the wonderful thing, they can never be anywhere in between the orbits. All right? And incidentally, this is still understood to be the case today. So, what I just spoke was gibberish, right? Hear it again. The Bohr model put the neutrons and protons together in the center of the atom. Makes good sense. Fine. There they sit. And suggested that electrons can jump into and out of other orbits By absorbing that energy, remember we mentioned it just a second ago with regards to adding energy, but they can never be anywhere in between. All right? You know, that sounds a whole lot like a mystery to me, something that once again science at this point in time is unable to explain. All right? Because it exists this way, at least the testing indicates that it does. But we have no way to explain how that's true. All right? That sounds a little bit like what some in the unbelieving world suggest of us who talk about a God who's three persons in one substance, one God. You know, I can't explain that, and no one ever will until we meet him face to face. But the reality, I mean, maybe even then, I mean, he's infinite. So, the fact of the matter is, this life has mysteries to it. Whether it's theological mysteries or scientific mysteries, mathematic mysteries, that's just the case. And so, you know, it's okay to understand and say to yourself, well, there's just some things that I don't understand. And then it's also a good thing to pursue understanding them as well. That's the process of science, right? But in any respect, that is a true statement. We don't know how that's the case, but they're never anywhere in between those orbits as depicted on page 226, figure 710. All right? Let's move on. When electrons move from an orbit close to the nucleus to an orbit farther from the nucleus, those electrons have been excited. Oh, here I go! I'm out of my orbit into another one. But I wasn't at any time in between the two orbits. But here I go! I'm in between the two orbits now. And it does it because it's been excited, absorbing energy. When the electrons lose the energy, though, I'm gone now, I'm done, and starts to move back closer to the nucleus, back to its usual, and we say that again with some bit of caveat, but it moves back to its orbit, it's described as being de-excited, okay? So on the way to Disney World is, woohoo! I'm excited! And on the way home from Disney World is, oh. All right? So, de-excited versus excited. Next statement. When a substance is heated and absorbs that energy, it emits light. And the atoms have gained energy to move into orbits further from the nucleus, and it's determined to return to the original orbit. It releases excess energy in the form of light to return to the original orbit. All right? So, that pretty color that scientists, astronomers see through telescopes, measure using a spectrometer, that they say, well, you know, that's what used to make up that planet. It's in the or star. It's in the process of burning up. Well, what's going on is those electrons that make up that stuff are being de-excited and emitting that energy in the form of light. All right, and it's that pretty color. That is the reason for the beautiful display. All right, is the electrons got excited and moved to a higher energy level, and now they're being de-excited and they're throwing off that extra energy in the form of light. All right? So that's kind of a lot. We just said a lot, but does it make sense? I mean, it just kind of is. All right? That's the way it works. Questions about that? Okie dokie. Well, that's good. All right. Now, let's read this. The quantum mechanical, the introduction to this is on page 228. And your notes, again, is what I'm interested in you knowing. Great stuff to draw. Always extra credit. Great stuff to draw. Great reminders for you in your future here. The quantum mechanical model of the atom. it's more complicated than Bohr. Electrons orbit not just in fixed circles like planets around the sun, but in orbit clouds called orbitals. All right? Think about a dog, think about your dog staked to a leash, staked to a stake outside on a leash, all right? And it's one that allows the dog, the leash doesn't wind up around the stake, all right? It allows it to eat, to do what it does all the way around. So if the dog wanted to go at the fullest length away from the stake and go round and round and round, it could. And a lot of them do, all right? They wear paths that way. But it also allows them to go anywhere within the diameter of that circle that they're able to form by pulling on the leash or the chain, right? So do you get the picture? That's the idea of an orbital cloud as opposed to just an orbit, all right? If one of the planets get out of orbit, I think conceivably there's trouble. But a dog changing its place in terms of its electron cloud on the leash around a stake, that's not a problem. And that's the way electrons exist. They're in the forms more of spheres, all right, than they are as circles, two-dimensional circles, all right? So an s orbital is the simplest. It is spherically shaped. You have one orbital for each energy level. Electrons orbit close to or far from the nucleus based on their energy. The 1s, so you see that depicted there in terms of figure 711. The 1s is smaller and has less energy than the 2s, which is smaller and has less energy than the 3s, and on we go. All right? I tell you what, hold with me on this stuff, and I tell you what, son, you've got your mask on. Would you go ahead and pass this stuff out, one to each person? You should have 1 page of extra credit and 1 page of test, all right? And I'm going to continue because we're going to need the whole test time. Golly. I'll quit at the time and I'll call your name if you want to come for your tests. Here we go. So turn over to page 230 and look at the p orbitals, all right? They kind of look like pairs, but as it turns out, they're kind of like three-dimensional pairs attached to one another, all right? And they're orbiting in terms of the nucleus there in ways that, well, again, you can see them. They're not two-dimensional in a perfect pear shape. They're all over that pair cloud in terms of their orbit. And listen to the description of the p orbitals. It's dumbbell shaped. I prefer pair. There is no p orbital in the first energy level, all right? So the first energy level has only an S shape to it, just a sphere, all right? There is no 1p, in other words. The first orbital, p orbital, is 2p, and there are 3 different p orbitals in each energy level. And so that is the difference between figure 712 and figure 713. That's describing the p orbitals in each energy level. So each one of those dumbbell or pear-shaped figures represents an electron and it's orbiting, okay? Everybody's got 1 page of test and 1 page of extra credit, right? We good? Well, we almost do. Thank you, son. Then the last thing, the d orbital. And as it turns out, the d orbital is complex. I know, I do it too. There are 5 different d orbitals for each energy level. The first and smallest, though, is located on the 3rd energy level, all right? So the first energy level contained only the S. The second energy level contains S and D. The third energy level contains S, P, and D. All right, I said only D on the second one, and I'm sorry, it's P. So here's the way this thing works, and what I'd like you to do is turn over to page 233. There is a quantum mechanical view of the neon atom, and neon, of course, is neon 22. So in terms of this thing, within the same atomic energy level, the different shaped orbitals require different amounts of energy. S requires the least, P requires more energetic electrons than S, and D require more than S and P. Each orbital, S, P, or D, can only hold 2 electrons. After 2 electrons, the orbital is full, and any new electrons must fill another orbital, must fill the next one to be full. We good? Yeah.
Extra?
What's that?
They're usually extra?
Yes. Yes, sure is. Thank you again, son. So, in terms of this thing, this is the way they do it. S orbitals can contain a total of 2 electrons per energy level. P orbitals can contain a total of 6 electrons per energy level. There's 3 orbitals times 2 electrons. D orbitals can contain a total of 10 electrons per energy level. That's 5 orbitals times the 2 orbitals each. Turn to page 4. All forms of matter try to stay in their lowest possible energy state. Remember, they get excited, but they always want to calm down back to the lowest energy state. Adding energy or heat causes the electron to travel to an orbital farther from its nucleus. It emits light and goes back to the original because it wanted the lowest energy state. The ground state is what you call the lowest possible energy state. Now, here's the coup de grace, and we're going to get there, but we're going to have to rush. If you have questions about this stuff, and I could certainly conceive that you might, because we're not going to be able to spend the time that I wanted to, but call me or text me, or, well, don't text me because I don't text very well, but email me, and I'll get back with you and we'll walk through this stuff. Get your little goodies here. Look at your periodic table. All right? There's lots of beautiful information about this thing, right? Well, we are just about to discover something really beautiful, and that is this thing shows you energy levels, and it shows you the different shapes of the orbitals. Now, that don't look like spheres and pears to me, but that's actually what it is. All right? This thing shows you the different energy levels and each individual shaped orbital and how they fill. All right? So, in terms of this thing, at the top you see hydrogen and helium. Well, there's your 2 electrons in the first energy level, and let's see. Yeah, look at, if you have it, if you're able to put your hands on it, you will notice in terms of this periodic table, these little numbers right here to the left, all right? They are indications, they are reminders of the energy level. So the first energy level is just a 1s-shaped energy level. It's got a grand total of 2 electrons. Remember, we said the atomic number reflects the number of protons and electrons. Well, hydrogen has 1 electron in that energy level. Helium fills it up. All right? But what about lithium, number 3? Well, it fills up the 1s energy level and that 1s-shaped orbital, and then it has 1 more electron, and it begins to fill the 2s orbital. And that is described by these blocks here in the left-hand side. those are the 1s, 2s, 3s, 4s orbitals. And with the exception of helium, which if you were going to be technical about it in terms of this, it would be sitting over in that row. But all of these electrons in terms of these columns represent the 1s electron. Notice on the right side, in the pink and the green on this one, there are 6 total in the blocks that go up and down. Voila! That's representing the total number of electrons that can go into a p orbital. So, in terms of boron, you filled the first 1s energy level in the 1s orbital with electrons. You filled the 2s orbital level and the 2s shaped orbital with electrons. And now boron has one more electron. It's beginning to fill the 2p orbital. All right? All the way over to neon, which fills that orbital. All right? In terms of the way these things fill, back to your notes because we're out of time. All right. Let me just read what you've got. And again, if you, I'll be shocked if you don't have questions. So the atomic number tells the number of protons and electrons. It also tells the electron configuration. That's the notation that lists the number of electrons that occupy each orbital in an atom. The electrons fill in this order, and this is crucial. So highlight this. This is how they fill. 1s, total of 2 electrons in the 1s. Next, they fill the 2s, total of 2 electrons there. Next, they fill the 2p with a total of 6. Now notice this. Next, they go to the 3s, and they fill a total of 2. And then they fill the 3p, a total of 6. All right? They fill the 4s, a total of 2. And then they fill the 3d. And that is the pattern. So please read through that. Remember, 3D requires more energy than 4P, so 4P fills up first, then 3D and 4P. I'm sorry we didn't get all the way through. Doggone it. Using the periodic table is faster and more accurate. The first 2 columns on the left side are the S's, which is what we just said. The next 10 are the D orbitals. That's what we didn't say. The yellow in the middle are the D orbitals. And then, of course, the ones to the right are the P. And the abbreviated electron configuration simply represents the the atoms nearest in terms of this thing. And we're out of time. You're going to have to read through there. I am sorry about that. And you know what? When it comes to your grade on the test, I'll be kind to you. But do your best on it. Call me if you have questions.